we start to talk about concrete. Just introduction. This week is just introduction. And we learned what we will expect to learn in this course: design of beams, slabs, column, footing, wall, pre-stressed concrete, and also software. We have three main components in concrete. Main components, three ingredients: coarse or fine aggregate, sand or gravel, cement, and water. The first step, water and cement, we have chemical interaction, which called hydration. If you have less water, we don't have a complete reaction. If you have more water, it will cause also another problem, probably segregation or increase the permeability of the concrete, whatever. So water is very important. You have to adjust how much water do you need. And also after pouring concrete, we need to maintain water content probably for 7 days after pouring concrete to complete the hydration process. We have something called setting time. We have initial setting, we have final setting. Remember, initial time is very important. Initial time is very important. For example, if you are constructing a building in commerce and the concrete will be prepared in Silver Spring, so probably we have at least 20 to 30 minutes traveling from this city to another city. So we need to be sure that the concrete will not set, because initial setting means concrete not it's not a liquid. After initial setting, concrete becomes viscous or more viscosity, or so you cannot reshape the concrete smoothly or in a very easy way. No, you cannot. So we need to avoid. We need to pour concrete before initial setting, the initial setting time. Curing of concrete for 7 days probably. So the main conclusion for all of these slides, we have three main components. We have cement, we have water, we have coarse aggregate, which is sand and gravel, fine aggregate and coarse aggregate. Okay, just to remind you for something I covered in another course which called hydraulics. Do you remember the hydraulic course? Do you remember something called gamma? Gamma, which called unit weight equal weight divide volume. So if you have two of them, if you have unit weight gamma is given, or you can figure it out, and you know what is the weight of this material, I can tell you what is the volume. Or if you know what is the volume and you know what is the gamma, I can tell you how much weight for this material. So unit weight equal weight divide volume. We have something also called specific weight. You remember something like this? Specific weight, which called G for a material, for cement, for gravel, for water, for anything. Specific gravity, sometimes called GS. Specific weight or specific gravity. Equal gamma divide gamma water. So if I tell you for cement, GS, specific gravity, equal 2.6. What is the meaning? It's dimensionless. We don't have the units. Dimensionless. What is the meaning of 2.6? Means gamma for cement divide gamma for water equal 2.6. You got it? So specific weight GS equal gamma for any material divide gamma water. So for example, if I tell you the specific weight for cement or specific gravity for cement equal 2.6. That means gamma for cement divide gamma of water equal 2.6. Okay, we still have two unknowns, gamma for cement and gamma for water. No, you have to remember gamma of water. Do you remember how much? 62.4. You have to remember this number all the time. 62.4 pound per cubic feet. So if this value, specific gravity, is given, I think it should be specific gravity. Specific gravity is given, I can figure out the value of gamma. If you can figure out the value of gamma equal weight divide volume. So if you have weight, I can figure out the volume. If you have volume, I can figure out the weight. We have first example in our course. We have a concrete mix. So we can expect three main components: aggregate, cement, and water. So we have a ratio between cement, sand, and the coarse aggregate. By weight, this ratio 1 to 1.6 to 2.6 by weight. Cement to sand to coarse aggregate. And also the specific gravity for cement is given. Specific gravity for sand is given. Specific gravity for coarse aggregate, which is gravel or stone, is given. I have question. If the specific gravity of cement is given, do you think I can figure out the value of gamma cement? I can figure out the value of gamma sand. I can figure out the gamma of coarse aggregate. Yes. How? Go back to my notes. Specific gravity equal gamma divide gamma water. So if you know specific gravity and do gamma water, I know it, multiply both of them together, I can figure out the gamma of this material. So if I bring my calculator and multiply 3.15 times 62.4 equal 196.56 pound per cubic feet. For sand, 2.62, which is the specific gravity, time gamma of water, I can figure out this gamma 163.5 pound per cubic feet. Okay. Gamma for coarse aggregate will be 2.65 times 62.4, so 165.4 pound per cubic feet. I didn't realize what's going on in this problem, but specific gravity is given for each material, so I can figure out the value of gamma for each material. And remember, gamma equal weight divide what? Volume. Okay. For this concrete mix, we will add water. And how much is given? Like 5.8 gallon or gallon per sack cement. And one sack of cement weight 94 pounds. If you have a sack of cement, the weight of this sack will be 94 pounds. It's standard. And we have air 3% by volume. Probably we have air inside the concrete mix. It will increase the volume by 3%. What is the required? We will produce 1 cubic yard of concrete. Can you tell me how much cement, sand, coarse aggregate, and water in this cubic yard? So we have a concrete mix in a concrete planet or whatever. We will add cement, sand, coarse aggregate, and water together. Can you tell me how much cement, how much sand, how much aggregate, coarse aggregate in the cubic yard of concrete? Step by step, one by one. Okay, the ratio between cement and sand and coarse aggregate is given 1 to 1.6 to 2.6. So if I assumed I have a cement equal 1 sake, which is 94 pound. If I add to the concrete mix only 1 sake of cement, which is 94 pound. So how much sand will be for this sack of cement? How much coarse aggregate? Okay, your sand will be 1.6, which is the ratio, time 94. 150.4 pound. How much coarse aggregate? 2.6 times 94 cement will be 244.4 pound. So if you have only 1 sack of cement, which weighs 94 pound, that means this sack of cement will need 150.4 pound of sand, 244.4 pound of coarse aggregate based on the given ratio. One more thing. Can you tell me how much water? Yeah, it's given. For 1 sack of cement, we need 5.8 gallon. This information is given. So anybody can tell me what is the relationship between gallon and the cubic feet? Yes, 1 gallon equal 0.134 cubic feet. So if you have 5 gallon, how much cubic feet? You can figure it out. It will be 5 times 1.134, so 0.67. So 0.67 cubic feet. The relationship between gallon and the cubic feet, as I told you, this one. 1 gallon equal 0.134 cubic feet. How to convert from gallon to cubic feet, because gallon for volume. Okay, one more thing. So this value will be 0.67 cubic feet. One more thing. Gamma water or gamma, whatever, not water, gamma equal weight divide volume. If I'm looking for volume, so volume will equal weight divide gamma. That's right. If you are looking for volume for anything, this volume will equal weight divide gamma. You got it? So I have weight for cement, weight for sand, weight for coarse aggregate. And I know what is the gamma for cement, what is the gamma for sand, what is the gamma of coarse aggregate. So I can figure out the volume for each component. For cement, 94 divide gamma of cement 196.56. This volume will be 0.478 cubic feet. Weight of sand 150.4 divide gamma of sand 163.5 will be 0.9192 cubic feet. So for coarse aggregate 244.4 divide gamma of coarse aggregate 165.4, this volume will be 1.5 cubic feet. So we have this volume of cement, this volume of sand, this volume of coarse aggregate, this volume of water. All of these calculations only if you add only for one sack of cement. Can you tell me what is the final volume? So one sack of cement will produce total volume of concrete. What is the final volume? Okay, add these volumes together. 0.478 of cement plus 0.92 of sand plus 1.5 of coarse aggregate plus, what about water? 0.67. So this one for cement, volume of cement, volume of sand, volume of coarse aggregate, volume of water. All of these volume, please add them together and multiply them by 1.03 to get the final volume. Plus 0.92 plus 1.5 plus 0.67 times 1.03, the final volume 3.675 cubic feet. I have question and I need answer. I have question and I need answer. Why? Thank you, Burak. Thank you so much. Why? Wait a moment. First question. Why I multiplied by 1.03? Why this number? And this number is constant for all problems? Any answer? Expansion, it's not expansion, but if you go back to your original information, the problem said we have air. If you are mixing concrete, if you are mixing these components together, we expect air inside this mixing. So the air will add additional volume. How much? 3% by volume. So after you add these volumes together, you can expect more 3% of volume due to the air component. So 1.03, I added or I multiplied the total volume of this ingredient by 1.03. That means I added extra 3% of air. For your information, I can convert from cubic feet to cubic yard. I think 1 cubic yard equal 27 cubic feet. So if I have 3.675 cubic feet, how much cubic yard? You can multiply this one by this one, divide this one. I can figure out the value. So 3.675 divide 27. This value will be 0.136 cubic yard. No, Brock, 1.03 based on the given. Sometimes the air percent is 4%. So I have to multiply 1.04. Sometimes the air component will be 2%. So I will multiply by 1.02. So based on the given. So this term related to air. So go back to the problem. How much, what is the percentage of air? Okay, so okay, your current situation is 1 sack of cement, which is 94 pound, can produce 0.136 cubic yard. Can you tell me if I'm looking for 1 cubic yard, how much cement? I think I can. Right now, we have 150.4 pound of sand. So 150.4 pound of sand produce 0.136 cubic yard. Can you tell me if I'm looking for 1 cubic yard of concrete mix, how much sand? I think I can. At this moment, we have 244.4 pound of coarse aggregate. For coarse aggregate, we have 244.4 pound. This amount of coarse aggregate produced 0.136 cubic yard of concrete. If I'm looking for 1 cubic yard of concrete, how much in pound coarse aggregate? I can figure out how much aggregate. So the problem is asking for how much cement in pound, how much sand in pound, how much coarse aggregate in pound to produce cubic yard of concrete. So the idea is this ratio. And I assumed we have only 1 sack of cement, which is 94 pound. So 94 pound will need 150.4 of sand based on this ratio, will need 244.4 pound of coarse aggregate based on this ratio, and the problem said 1 sack of cement need 5.8 gallon of water. I then convert this weight to volume, and water is already in volume, but I convert it from gallon to cubic feet. I added these volumes together, and don't forget to increase this volume by 3% for air. That means these weights will create this volume of concrete, or this volume, but I converted it to cubic yard. So this weight of cement, 94 pounds, will create this volume of cubic yard. Can you tell me how much weight of cement to produce 1 cubic yard? I can figure out. This weight of sand created this volume of concrete. So can you tell me how much weight of sand to produce 1 cubic yard of concrete? And so on. So finally, I can figure out how much weight for each component to produce cubic yard, 1 cubic yard. So the main idea in these calculations to remember that gamma, which is unit weight, equal weight divide volume. How can I figure out the value of gamma? Specific gravity will be given, because specific gravity for any material equal gamma for this material divide gamma of water. And remember, gamma water equals 62.4 pound per cubic feet. By the way, in this course, all of our problems, all of our study will be in US unit. So everything will be in pound or kip. Everything will be in feet, inch. We don't have Newton or kilonewton or meter or centimeter. No, everything will be in US unit. Okay. So the first part we covered is plain concrete. We have only cement, sand, coarse aggregate, water. Add them together, you can produce concrete, which is called plain concrete. Sometimes, not sometimes, all the time we add another factor or another material or another component in this mix, which called reinforced concrete. So we have steel bars, as you see here in this picture. These steel bars will create something called mesh, and then you add concrete. After setting or after hardening of concrete, you will get a new material which called reinforced concrete. Cement, water, sand, coarse aggregate, and reinforced reinforcement or steel rebars. Why? Why steel rebars? To answer this question, we need to study this course. Why steel rebars? Why reinforcement inside concrete? How much? How can I get this reinforcement? This question will be answered during this course, because this course will answer only one question. How much steel reinforcement you need in your design? Why we need steel reinforcement? Do you think this steel reinforcement is enough? It's too much? It's too low? We need to answer all of these questions during this course. Okay? So we have reinforced concrete if you add steel reinforcement. We have another shape or another product of concrete which called pre-stressed concrete. I can explain this figure here. Guys, what do you think if you have cable? This cable is pulled from this side and this side by a force F. If you have a rubber band, and you stretch or you apply a tension force on this rubber band, what do you expect? But rubber band is a very, very simple example. But if you are talking about a steel cable, I'm talking about not you, not a person here will pull this one. No, I'm talking about equipment. I'm talking about hydraulic jack. There is different. But in a very simple example, if you have a rubber band and you stretch this rubber band, I expect elongation in this one. That's right. So we have very, very, very strong steel cable pulled from this side and this side. So we expect expansion, stretch of this cable right now at this moment. You are talking about huge amount of force. Then at this moment and during this stretch, I build formwork and I poured concrete. Concrete is liquid at this moment at pouring. Concrete is liquid. And the steel cable is stretched. Remember, the steel cable is stretched. And I poured concrete. Concrete is still liquid. I wait for probably 28 days. The cable still stretched. Probably not 28 days, at least 7 days. So the cable is still stretched. And the concrete became hard after 7 days, not liquid. At this moment, I will cut this cable from this end and cut the cable from this end. What I mean, I released my force. I will not apply any more force. What do you expect? Remember, this cable was stretched like rubber band. Once you released the force, what do you expect for this steel cable? This steel cable would like to go back. About the problem, do we take the volume of air out before making the final calculation? Since air is 30%, do you take 3% out of the 1 cubic, then use the value to get sand? I think it should be the same answer. Yeah, the final answer will be the same, but in different way, Cody. Your question, it will be the same, but I recommend to add 3% from the beginning because air is a component like sand, like cement, like water, like coarse aggregate. So I recommend to add air from the beginning. Don't wait until the end. Add air like cement, like you add cement plus water plus sand plus coarse aggregate. Go ahead and add air. Then you can get the final answer. Okay, I recommend this. Probably your suggestion will get the same answer, probably not the same exactly, but very close. My question is right now, what do you expect from this steel cable to do on concrete? This steel cable would like to go back to the original position. So I expect the final situation is this cable will apply compression on concrete. Because this cable would like to go back. But we have a bond between concrete and the cable. So concrete will not allow for the cable to go back. So the cable will apply compression on concrete. Do you agree? Okay. So let me talk about concrete without cable. If you have a beam between this support and this support, and you stand here, what do you think about this concrete? Will this concrete would like to break? Will be broken? I think concrete will start to crack at this location. So we have tension here. So if you have concrete without pre-stressed, and you are here, I'm talking about you as example. So I expect this beam will be broken at starting from this location by tension. What do you think if we add pre-stressed? I think that cable here will add compression. So I think this compression will reduce, will close this tension crack. That's right. So your beam will be good. This beam will support another person, probably many person, because only one person break this beam without pre-stress. If you add pre-stress, and that means you add compression, that means this crack will not happen, so you can add more people on the beam. This is the main idea of pre-stress. We will cover this later. What is the meaning of pre-stress, and how can we calculate how much force you need to pull out the cable? Okay, so this is the main idea of pre-stress. Remember, the original force in the cable is tension. I am stretching this cable. Then I poured concrete. Then we have very strong bond between concrete and this cable. Once I released this cable, the cable will apply compression on concrete. So we start first with the tension force on the cable without any concrete, but finally this cable will react to concrete by compression force. This is the main idea of pre-stressed. And these videos you can watch how can we apply this force. You will find hydraulic jack. These jacks are very, very strong and very, very dangerous. Be careful. Because you're applying very, very huge amount of force. For any reason, if something wrong happened, you can expect for releasing of this force, you can expect a dangerous situation. Probably the hydraulic jack will move away. Probably the cut in this cable will happen if this cable was broken during pre-stressing. I believe anybody around this cable will die. Okay. So the main idea, if you have concrete without pre-stressed, we can expect cracks. If you add pre-stressed, these cracks will be closed due to the compression force applied by the cable. For fresh concrete, if the concrete is fresh, still liquid, we have some, as you remember, we have water added to cement, added to sand, which is fine aggregate, added to coarse aggregate. That's fine. So you have to add these components by very specific ratio. What will happen if you add more water? What will happen if you add more sand? What will happen if you add more coarse aggregate? You are engineer during the construction. So how can I judge the concrete mix is perfect? to pour my my project, or reject this concrete mix. Yeah, I'm engineer. I can reject. Hey, stop! This concrete is not good. So how can I judge? We have some experiment. The first one, which is very important, concrete slump test. Based on the result of this test, I can tell you this concrete mix is good. No, this concrete mix need more water. No, this concrete mix has more water, so I will reject it. I cannot accept this mix. So you can reject it and tell the truck to go back to the concrete company. So this one is very simple. You have a cone like this one, and you add concrete inside this cone, but you need to add concrete by 3 layers. The first layer, 1/3, and using a steel rod to compact this layer. Then add the second layer of concrete, the second third of height, and then with the steel rod, go ahead and compact the second layer. Then add the third layer to fill the cone, and using the steel rod, I think with 25 times, you can compact the third layer. Go ahead and remove. Once you are done with the and you fill the cone with concrete, go ahead and level the surface, remove any extra concrete, and remove the cone, the steel cone. If you remove the steel cone, what is the height or the difference between the height of the original cone and the final shape of concrete? Based on this height or this difference in height, you can judge this concrete is good or not good. The common range is 1 to 2 inch. This concrete will be very dry concrete, and you need to add some water. The normal range, this difference in height will be between 6 and 7 inch. But remember, if you removed the steel cone and you find this shape or this shape, you have something wrong in the concrete mix. Something wrong. One component is very is too much. But the optimum or the ideal shape after you removed this cone, this one. If you have shear collapse, or you have completely collapse, this one due to more water, you have too much water. I think this one you have very bad component, very bad ratio between sand or coarse aggregate. But the optimum or the ideal shape is this one. So you are engineer, you are waiting for the concrete truck. Once the truck is arrived to the site, so you can check the concrete by slump test. Okay, so the actual video for slump test, you can watch this one. Unfortunately, last semester or last year, I did all of these experiments with the student on our concrete lab. We poured concrete, we did slump test, and we get the results. So I'm so sorry for this semester. So you can watch the video using this link. After concrete is hardened, the concrete is very hard, probably after 28 days. I can judge the concrete strength by something called compressive strength test, or compression test. You can pour concrete cylinders, and these cylinders will have standard dimension, probably 4-inch diameter and 8-inch height, or 6-inch diameter and 12-inch height. This one or this one. Pour this concrete, wait for 28 days, put these cylinders under the compression machine, apply force until you break this cylinder. How much this force? If you divide this force by the area, the cross-section area of the cylinder, you can get stress. This is stress called compressive strength of concrete. I will talk about this one more time next time. Let me stop here for today, and I will continue next time. But before leaving, yes, 25 compaction per layer. That's right, Oliver. Anybody has any question? Please, at home, watch these videos to understand correctly what's going on with the slump test, and also pay attention to the problem I solved today. This problem is a real problem. You have a concrete mix with these with these ratios, and you need to figure out how much cement, sand, coarse aggregate, or water can be added to get finally 1 cubic yard of concrete. This problem is a very real problem. I believe in another course, probably with cost estimating or something like this, you need to figure out how much the quantities of any material to construct any building or something like this. So this type of problem is very important. You need to figure out how much component do you need in your concrete mix. Okay, so this problem is very important.